click save, and once you click start, the recorder starts. Okay, and you can tell whether the recorder is starting or not by the time here, because if you see the seconds ticking, that means that the recorder is working. Now this is a great tool. Okay, how many people have like lots of space left on your hard drive on the computer where you do most of your development? Okay, so one thing you can do is to record your development sessions. Okay, not only for this class but also for your other classes. So when you sit down to do your homework, especially with programming, you just do something like this. Okay, it might chew up some space. Maybe 1 or 2 gigabytes per hour or so. Okay, but these days we have what, terabyte hard drives. So a few, 1 or 2 gigabytes is not really that much. Okay, it's not going to make a big dent on your storage. But the nice thing is now you have a recording of your entire development cycle. So in case you run into a problem, like, okay, this is my program, it's running in a very strange way and I have no idea of how to debug the program at this point. Okay, so what you do is, with a hybrid class like this where we don't have a lab session, that's face-to-face, what you can do is to use a simple tool. Okay, you can do it in YouTube as well, is to upload the entire video onto YouTube, and then you just go to a particular time frame and right click and I think you can give me a URL with a particular starting time, send it to me and say, okay, this is my recording of my testing of the program, and at this particular timestamp I'm running the program in a certain way and the program is crashing. I have no idea how to proceed at this point. So this way you don't have to describe in words what is happening, what you click, what you enter, how you run the program, because the video will show me exactly what you did. Do you see the advantage of doing that? Yep. That's going to be too big. Yeah, so that may not be the best way to do it, to send the entire file to me, but you can select like a 45-second portion of it and just upload it to YouTube and just send me a link to the YouTube video. Then I still have access to it. Yep. If you have a Google account, like a regular Gmail account, you already have a YouTube account. Not sure about the apps account, whether that also gives you a YouTube account. Does anyone know? No one knows? No one's curious? When you sign into YouTube, okay, once you sign into apps.losrios.edu and then you sign into YouTube, does it give you like the interface of already signed into YouTube? Maybe not. I'll be kind of surprised if it does, but something that's worth trying. Okay, so what we'll do today is we'll go ahead and kind of move on. We'll talk about the exam on Wednesday. And we have quite a few topics to continue to talk about in this class, and we are going to run, we may run out of time for this class too, for that. Last time we talked about modular programming, and I kind of explained what is modular in this case. Not sure whether we touched on functions. I think we did. I don't think we did. Did we talk about functions, this particular slide? No? Okay, so this is a good time to talk about functions. So functions or subroutine is a very, very important topic in any programming language. So the concept of using a subroutine is going to be useful regardless of whether you will write another program in C++ after this class or not. Because functions exist in basically all known programming languages have functions or subroutines. So what a function is in C, okay, let me just kind of roll back a little bit. How many people are not familiar with the concept of a procedure, a function, or a subroutine? They basically mean the same thing. It's just in different classes. Different people use different terms to refer to these things. So are we okay in terms of the concept of a subroutine from the CISP 301 or 300 class? Is that part okay? Okay. So having that assumption, we don't have to talk about the actual concept of a function. We can actually jump right into the syntax of a function in C. So the way we define a function is it has 4 main parts. The first part which is before the entire definition of a function, is called the return type. Now the return type is actually not optional. So even though I mentioned here that it is optional, it's not really optional. In other words, you always have to specify what is the return type of a function. It is somewhat optional in the sense that if you don't specify a return type, it is integer. Okay, so the C++ compiler actually says, okay, if you don't tell me what it is, I'm going to assume it is an integer. But if you turn on all the warnings, you most likely will get a warning out of it. Okay, because it's just not a good idea to let the compiler decide what is the return type of a function. The second part is the name of the function, which is also called the identifier in C and C++. It's just really a name. Okay, this is how you identify a function. Now in C and C++, you cannot reuse an identifier for multiple purposes. In other words, if you use the name, let's say ABC for a function, you can no longer use ABC as a variable name. Okay, so you can only use it in one context or another, cannot be used in multiple contexts. The third part is a list of parameters, and this can be empty, but even though it's kind of rare to have an empty list of parameters. So in this particular case, this has two parameters. X is an integer type, and y is an integer type, and they're both parameters passed to function f by value. Okay, if you don't see an ampersand in the parameter, it is passed by value. If you see an ampersand, it is passed by reference. And the rest of it, which is starting from which is a block. Okay, it's a block statement all by itself because it starts with an open curly brace and it ends with a closed curly brace. This part is the body of the definition of a subroutine. In other words, when the function or the subroutine is called, this is what is being done. And that's basically the four main parts of a subroutine in C and C++. Are there any questions about? Yep, go ahead. Subroutine is one, procedure is one, function is what C calls it. Yeah, in Visual Basic it's called subroutine, and that's another common term that people use. All right. So, are there any questions about this part of the discussion of what is a function? Okay, any questions? And we can kind of move on here. Okay, the return type is kind of important because the return type tells you where we can place an invocation of this particular function. In other words, in this case, because the return type is int, which stands for integer, that means the invocation of the subroutine can go anywhere where an integer is expected. So tell me just a few examples of what you can use an integer for in a C or C++ program. Sorry? For math. Okay, so arithmetic operations like addition, subtraction, multiplication, and division. Okay, and it is true. Okay, the invocation of f in this case can be on either side of multiplication, division, addition, subtraction, or just about anything you can do with an integer. Comparison. Okay, you can compare, the invocation of a subroutine to 0, for instance. Okay, you can do that too. And here's just an example. Okay, the invocation of f is now the left-hand side of a comparison. So assuming x is also an integer, this is perfectly okay because I'm just comparing an integer value with another integer value, which is fine. There's no problem. Another example is here. Assuming x and y are both integers, you can use f, x, y, the invocation of subroutine f with parameter x and parameter y on the right-hand side of a plus equal operator. That's perfectly okay because assuming y is an integer, the return value of f is also an integer, and that is certainly one place you can put an integer value. So the return type of a subroutine kind of dictates where you can put that particular, an invocation of that subroutine. Are there any questions about how a return value is used? Question? Okay. the way the function works is like this. Okay, I kind of like to explain how.
Yesterday, I was driving on Highway 20 and Highway to Redwood Valley, which is kind of far away from here. And in the middle of nowhere was a woman carrying a gas can to try to walk to the next gas station. That's gonna be tough. And it's not just a small can.
It's working. So we're back in business. It's good. It's better to have these things on using rechargeable batteries instead of these not rechargeable batteries, and just have a little charger here to kind of keep a few always charged. And if I pop these two out, I can put it back into the charger, and it'll be ready next time too. But this is still okay, and I can toss these away. All right, so getting back to what I was talking about, I like to explain how things work in addition to, what you use it for, because once you understand how it works, hopefully, you will have an easier time actually making use of it. So at compile time, which means, the translator, how does a translator look at a function? At compile time, the definition of a function, which is, the part that includes the open and close curly brace, generates a block of code corresponding to the body, and an identifier, which is the name of a subroutine, is used as a key to locate the code. In other words, you use the name to find the body, of the subroutine. The invocation, as opposed to the definition, the invocation, which is where you actually call the subroutine of a function, causes a compiler to look for the block of code corresponding to the identifier of the function that is being invoked. So using our example here, this is the definition of a subroutine. It tells us exactly what the subroutine is supposed to do. This is the invocation of the same subroutine, which is at this point, I want to trigger those operations. Is that okay? Does everybody understand, what is the definition of a subroutine as opposed to the invocation of a subroutine? Is that okay? All right. In the case that the function is not defined in the same source file, the compiler will still do its job, but it will insert a stub in place of the actual invocation of the subroutine. It will leave a stub in the object file corresponding to the unresolved reference to a subroutine. So let me give you one example of what this is, what I'm talking about here. And let's switch to a command prompt. I forgot I'm not using Linux. Okay, I can still do it, Well, I don't have to run the program. I can just, show you the code and not have to run it. Okay, so let's go ahead and do it like this. All right. So let's just say that this is my entire, program, which is obviously not very useful. Okay, so I'm invoking the subroutine G and just return 0. This is what I have in main.cpp. This is the entire program. So what the compiler is going to do is complain this time. Okay, the compiler is going to complain because, hey, what is G? Nobody told me what is G and how G is supposed to be used. So the compiler doesn't like that. It will just complain about it and go like, can't do this. So the first thing we need to do in this program is to tell the compiler and say, okay, this is what G is. Okay, this is the proper way to call or invoke G. G does not return anything, so void as a return value simply means there are no return values. Okay, it doesn't return anything. And you can leave the list of parameters empty to basically say it does not take any parameters either. Oops, I take it back, sorry. Okay, this is it. So instead of using open and close curly brace and put some code in between to tell the compiler what G is supposed to do, this is called a prototype of a function in C and C++. So what a prototype does is to tell the compiler how to make use of a function without telling you what the function actually does. Okay? Is that or how it works? Does everybody understand what I just said? How to make use of a function, but not telling you the details of how the function works. It's kind of like on a remote control. Okay, so remote control is really useful for many analogies. It's just like with a remote control. When I press the on/off button here, okay, I know what it is supposed to do. Okay, that's the prototype. Okay, the prototype means if I see that symbol, with a circle and a bar, that's an on/off button, and if I press it, it will just toggle the on/off state of whatever I'm trying to control. But what about the actual circuitry of turning on and off the projector? The time delay so that the fan will run for a little bit longer, to cool down the lamp before the whole thing shuts down. This button doesn't tell me anything, right? Okay, that's the implementation detail. So that's what a prototype is. A prototype is really a remote control. Looking at the button, you know what it is supposed to do, but not necessarily how it is done. Is that okay? All right. So as far as the compiler is concerned, it is now happy because the compiler says, okay, great, somebody told me that G does not return a value and it does not expect any parameters. Great. So by the time I get to this line here, the compiler says, oh, okay, I know this is okay because I'm not trying to utilize the return value of G for anything, which is good because G does not return a value. And I'm not passing any parameters to G, which is also good because G is not expecting any parameters. So as a result, the compiler is fine with this. But where exactly is G? Who's defining G? The compiler does not care. The linker would, but the compiler does not. Is that part okay? So having this in a particular file, I can now have a different file. Okay, I can have a separate file, and the content of that second file can be just this. Okay. So this is, and which means the compiler will now have to compile this source file separately from the one that contains main. Which also means the file will give me a different object file. So each object file is kind of individual. They don't know of the existence of each other, and the compiler has no concern about by the time this program runs, is someone going to define G? The compiler doesn't care at all. It just assumes that somebody is going to define G by the program runs. So one component of the development tool chain that does care about whether G is really defined or not is the linker. So what the linker does is it will take the object file corresponding to this source code, it will take the object file corresponding to this source code here, and by the time it links, then it will ask the question of, are all the unresolved references cross-referencing resolvable? That's what the linker is going to do. So the linker will look at the object file corresponding to this source file and say, hey, you know what, this G here is not defined within that file, and it will ask the question, who has the definition of that G? But the linker is also getting the object file of the second source file, which does define the label G. So the linker will make the association and say, oh, you know what, now that we know G is here, I'll update the reference of G over here, and then we won't have a problem because it is now resolved. Do we have any questions about the process of compiling as opposed to linking? No questions? Okay. So at runtime, not link time, when we run the program, what is really going to happen? The definition of a function does not do a single thing by itself. In other words, you can have 20 gazillion of these things, okay? If a function is not getting invoked, if it's not getting called, nothing is done. You can have any code here that can be problematic too. But if it's not being run, it's not going to be, there won't be anything happening. So what that means is, in order for a function to do something, it has to be invoked. There has to be a call to the function somewhere in order to trigger the execution of the function. Yes?
So unlike an assignment system, like in F or something, we don't use that. There's going to be a problem with the policies. X not being used at this point.
It will complain when it compiles. If you have a syntax error or any type of problem in a function, the compiler will still do its job and complain about it. But if you have a logic problem, it's not going to bother anyone, because if the function is not getting called, then the logic problem is not going to show up either.
So the function can be defined and not called, then won't be able to.
No, it will complain about it if it has actual issues. Okay, I'll give you an example here. So let's say we have a function f here, and I'm actually defining it here. Okay, and let's just say that f refers to a particular variable, v equals to 0. Okay, so if I don't declare v anywhere in the program, the compiler will complain about it and say that where is v? So it will be compiled. The translator will do all the type checking, okay, and all the stuff that the compiler is supposed to do. But if you have a logic issue, like a logic problem, and that won't be a problem, because if a subroutine is not being called, it's not running. If it's not running, any logic problem is not going to show up.
Okay, so if you have in V,
Mm-hmm.
and then you have V equals 0,
Right.
then you call, then there's no call for F.
Well, the compiler won't complain anyway. Okay, so whether the compiler complains or not has nothing to do with whether the subroutine is called or not. Yeah. With a scripting language, on the other hand, that really is the case. With a scripting language, if a function is not called, then it won't even check whether it has problems or not. But with a compiled language like C and C++, it will still compile it. It's just that it's not going to be executed. Alright, so at runtime, the definition of a subroutine the definition of a subroutine does not do a single thing all by itself, because it's just a definition. It has to be invoked from somewhere in order for that code to start to execute. When a subroutine is invoked or a function is invoked, these things will be happening. The first thing is space is allocated and values will be initialized for the parameters. Okay. Our example here illustrates exactly that. Okay, this is the definition of a subroutine. It's expecting 2 parameters. So when execution gets to this point of a program, this is just a portion of a program. But if execution does get to this part of a program, what it will do is it will associate the first value to parameter x. It will associate the value 3 to parameter y. Okay, that's the first step. So the parameters will come into existence and have the initial values initialized. The location of the next step is going to be saved. That's the second step. Now, this is the one that is really hard to illustrate, because in the sample code that we are dealing with here, function f, or the invocation of f, is in the middle of an expression that is used as a condition in a conditional statement. So I can't really tell you the line number of where it's coming back to when the subroutine is done, because it is still on line 1. Okay, I can only tell you that it will come back to line 1 to finish what is left on line 1 to do. Is that okay so far? Okay, what step 2 does is, before it continues execution in the subroutine being called, it will remember what else it is supposed to do when the subroutine is done and come back to this point. Is that part okay? Okay. So in this case, we'll come back to evaluate the equality check when the subroutine f is done. So now on to the third step. If a subroutine has any local variables, at this point in the third step, the local variables will be allocated and optionally initialized. Okay. And then continue execution in the subroutine, starting from the very beginning. Okay, Tack, I have a question. What if we are in that subroutine already? This is a recursion. Doesn't change a single thing. Nothing at all. Okay? So we always go back to the beginning of a subroutine when we invoke a subroutine, even if it is a recursion. Okay, so let's say the subroutine works fine. We are now at the end of the execution of a subroutine. What is going to happen when we execute a return statement? Well, a return statement, depending on the subroutine itself, can have an optional return value. A return value, which is a value that you put on the right-hand side of the word return, can only be there if the return type of a subroutine is not void. Okay, that's the only time you can specify a return value. If the return type of a subroutine or function is void, then you cannot return any particular value, because you just told the compiler, I'm returning a particular value, so why are you specifying a value with a return statement? So in those subroutines, return all by itself in a semicolon is going to be the only thing you can do. You cannot specify a value to return. When you return from a subroutine, local variables will be deallocated. In other words, every local variable that is allocated at the beginning of a subroutine, at this point they will be quote-unquote deallocated. Now the word deallocated is kind of confusing because in a way it seems like we're recycling something, okay? But that's not really the case, okay? It simply means those variables will quote-unquote cease to exist. The lifespan has come to an end. The next time you call the subroutine, it won't be the same values anymore. So every time you invoke a subroutine, the local variables start with some random quote-unquote new values. Occasionally you will see that, hey, but it is the same as last time. Yes, you can observe that sometimes, but you cannot count on it. Okay, so there are no specific initial values related to local variables. And then at that point, after this, after step number 2, execution will continue at the location that we saved a little bit earlier. So in our example here, when f returns, then we'll continue to evaluate the equality, because that really is the next thing to do after the subroutine f has returned. And also, local arguments will now be deallocated, the parameters will be deallocated, and the optional return value will be utilized. In our example here, f is supposed to compute the sum of the two parameters. So at that point, this particular value will be utilized. 5 basically will be used to compare to x. Are there any questions about this part of a subroutine? Questions? Okay. The key is we are doing all of this stuff here on a per invocation basis, not on a per function basis or per subroutine basis. Now I cannot emphasize that difference enough, because that is why people, that's why some people can understand subroutine call but not recursion. Okay, and it's not uncommon at all for someone to say, oh, I understand subroutines, I have no problem knowing how to define a subroutine, how to make use of a subroutine, but when it comes to recursion, go like, oh, I have no idea what is happening here. Okay, that misunderstanding has to do with the association of local variables and parameters on a per function basis instead of the correct way of looking at it, which is on a per invocation basis. Every time you invoke a subroutine, you have a new set of parameters, a new place to return to, as well as new local variables at the same time. Are we kind of doing okay so far with those concepts? So at this point, okay. So let me show you one example, and you can tell me whether you find it confusing or not. The first one should not be confusing. So the first one looks like this. Okay, so we have int f1, and it takes an integer I, and all it does is the following. And I'm not going to use any tricky ternary operators here. I'm just going to use a conventional conditional statement. And all it does is to say if I is 0, I equals to 0, and following, it will just go ahead and return 0. Else, I have to specify something here. It will also return 0. Okay, so it's going to return 0, regardless. Is that okay? Completely useless, subroutine, because it's going to return 0 regardless, right? Because the then statement returns a 0, the else statement also returns a 0, so regardless, it's going to return a 0. Are there any questions about this one? No? Okay. So the next one is going to look like this, okay? And so we are dealing with another subroutine that returns a value of an integer. This is called f2. Same type of parameter. And inside this one says if I is equal to 0, it's going to return 0. Else, it's going to call f1. Return f1 of I minus 1. Okay, there we go. So let me just change the size of the editor a little bit. Any questions about these two subroutines now and how they relate to each other? F2 has the potential ability to call F1. F1 does not call anyone. Is that okay? No questions about this one? Okay. So I'll go one more step. Okay, I'll just do one more step here. And we'll have F3. So F3 is not going to be that fancy either. And all it does is basically doing the same thing as F2, except F3, if you pass an I, parameter I that is non-zero, it's going to call F2 with the parameter of I minus 1. Are there any questions about the three subroutines at this point? F1, F2, and F3. Go ahead.
Can F2 call F3?
Can F2 call F3? Not the way it is structured right now.
Because I was trying to make a program over the weekend and using subroutines, and it was like the lower could access the top ones, but not vice versa.
That is correct. In C and C++, if you try to call a subroutine that is not defined at that point, you have to give the compiler a prototype first. Remember the prototype, which is replacing the body of a subroutine with a semicolon? That is what you need first.
Like
Yeah. If you put that, in front of, ahead of F2, then F2 can call F3.
oh, okay.
In other words, in this particular case, if I do something like this, which is a prototype, which is just telling the compiler to call F3, it needs one integer parameter and it returns an integer. As soon as you have done this, then F2 can call F3.
Okay, and that's all in one file.
In the same file, correct. Okay, so when you look at F3, it looks kind of like F2, except F3 calls F2. And when you look at F2, it calls F1. And when you look at F1, it's about the same, except it doesn't just return the value of somebody else, it just returns a 0. Is that okay so far? So in your mind, when I call F3, let's say with a value of 2, okay? Okay, so let's imagine this, okay? Let's imagine we are calling F3 and I'm passing a parameter of 2. So the first thing we do is we get to the conditional statement here, is 2 equal to 0? No, so we have to execute this one here, right? So when we call F2, what is the parameter that I'm passing to F2? No, it'll be 1 because parameter I is 2, so I minus 1 is 1, okay? So then we start execution in F2, right? And with a parameter of what again? 1, that's right. So 1 equals to 0 is false. We go to the else branch, so we execute the statement. And that in return will call F1, right? And what is the value of parameter I when I call F1? It'll be 0, but it doesn't really matter because either way it's going to return a 0. When it returns, it goes back to here, and that in return becomes the return value of F2, so F2 is going to return a value of 0, and that will go back to this point here where I invoked F2, so this will in return will become the return value of F3. So whoever called F3 to begin with now has a value of 0 to play with. Okay, you can use it for comparison, for multiplication, division, or whatever. It doesn't really matter. Okay, so if there are no questions about this calling hierarchy, let me change it in a way that uses recursion. Okay? So to change this to use recursion, I'm going to call this f by itself. So f has an integer I parameter, and all it's going to do is to say if I equals to 0, returns a value of 0. Just like that. But the else is going to be the interesting one, because I'm just going to say, hey, call f again with I minus 1, or return the value of invoking f with the parameter of I minus 1. Do you see how f is resembling the hierarchy of f1, f2, and f3? So why would there be a problem with f being a recursive subroutine?
I was less than 0.
Sorry?
I was
Oh,
less than 0.
yeah, if I is less than 0, it becomes an infinite loop because it will keep subtracting 1. But because integers eventually will wrap around, so after a long time, hopefully before the stack runs out, it will kind of come back, but that's not the expected behavior. But in terms of calling a subroutine from itself, f is no different from the hierarchy of f3, f2, and f1. So the concept of, but the recursion is hard to understand, has to do with how many parameter i's are we dealing with here, and how do we save where to go back to. Now, most people, when they look at f3, f2, and f1, they have no problem understanding, because hey, this is a different subroutine than this one here. So this parameter I has nothing to do with this parameter I. That's what most people think, because syntactically, visually, they are different. Okay, they're at different places, they belong to different subroutines, so most people would not have a confusion of, oh, which I am I talking about? Well, they're different I's, they're from different subroutines, and therefore there's no confusion. When they look at something like this, then there's a problem, because I'm calling f from inside f. F already has a parameter I, so when I go to the next invocation of f, am I not going to override that I? How do I get back to the previous I, and so on? That is the problem of recursion, because most people think there's only one parameter I, but that is not the case. Because every time you invoke a subroutine, there's a new parameter. So that means, in this case, if I call f with a value of 2 to begin with, there will be 3 simultaneous invocations of f, and each invocation has its own parameter I. The first invocation has parameter I being 2, the second invocation has I being 1, the last invocation has I being 0, which is basically what f3, f2, and f1 did. Are we kind of doing okay so far with the concept of recursion and why that should not be an issue? Kind of okay? Because this is going to be, recursion is most programming languages are capable of recursion. There are very few that cannot do recursion. And the biggest problem is not even the fact that, are we going to write a lot of recursive subroutines in all the other classes? And I can tell you honestly that in CISP 400, probably not much recursion. In CISP 430, which is data structure, yes, you will deal with quite a bit of recursive subroutines. What about at work? Probably not a whole lot. Okay, you need 1 or 2 cases of recursion, and that's about it. Excuse me. But the understanding of recursion is not really just about recursion itself, because there are other occasions where an understanding of the per invocation basis as opposed to a per subroutine basis is also going to be important. I cannot really quite name those scenarios or situations here. I can name them, but it won't be very meaningful to you. It has to do with the processing of interrupts or interrupt surface routine. Okay, in that context. The second one would be signal processing. Okay, so if you have a signal handler in a program to respond to signals, it will run into the same type of issues. And the third one is multi-threading programming, which is what most of you will encounter if you continue to become a software developer and have to deal with a multi-threading type of program. You probably have to deal with multi-threading. If you deal with multi-threading, whether a subroutine has one particular set of parameter and whether it is on a per invocations suddenly becomes a big deal. Okay. Does anyone want me to go into that for maybe 3 minutes just so that you can kind of see why it is an issue? Okay. Okay, so let's talk about multi-threading a little bit. Okay, I'm not going to take a lot of time, and this will not be in the final exam whatsoever. Okay, so if you're not interested, don't worry about it. So what is multi-threading? Multi-threading simply means the execution of program can now be separated into multiple threads. Okay. At this point of all the programming that we have done, it's called single-threaded. In other words, at any particular point in time, the program can only be at one particular place in the debugger. Okay, that makes sense, right? But in a multi-threaded program, you can separate the program into, let's say, 3 threads in this case. So we have thread A, thread B, and thread C, and they're all basically, points of the same program, the same process, but they're all running at the same time. In other words, in this case, thread A can be in file f.cpp on line number 16, while at the same time thread B is in g.cpp, line 23, and at the same time, thread C is in main.cpp on line, let's say, 65. So your program now has 3 quote-unquote fronts, or 3 places that it is actually quote-unquote at exactly the same time. Now, why do you want to write programs in a multi-threaded way? It will run faster when you have a multi-core processor. Okay? If you have a single core processor, it doesn't make any difference because it's just a pretense that you have multiple threads running at the same time. But when you do have a multi-core processor, then these things can actually happen at exactly the same time, which means your program runs faster if nothing else is consuming or utilizing all those other cores. So why does this have anything to do with recursion or a proper understanding of how local variables and parameters work? Well, let's think about it. Okay, so let's just say that. Okay, so this is the current example. Okay, so we can imagine that f is going to call a subroutine called sub1. Okay, so f calls sub1. Okay, no big deal. Any subroutine can call any other subroutine. And let's imagine sub1 is a very time-consuming type of subroutine. Okay, it takes a while to do the processing. You don't want the processor to be hogged by a particular thread. In other words, before sub1 is all done, or before thread A is at a point where you can give up control, the operating system like Windows NT or Linux or Mac OS X has a way of preempting what we call a thread and say, hey, you have used up too much time already. It's time to let somebody else run. Is that making sense? Okay. So sub1 is going to be very time consuming, and at some point, the processor or the operating system, I should say, comes in and say, hey, you know what, thread A, it's time to give up your control and let somebody else run. Okay, let's give it to thread B. Thread B now gets execution time and say, okay, it's my turn to run. And guess what? G is also going to call sub1. All right, is that a problem? Can 2 subroutines call the same common subroutine? It's not a problem, right? That's permissible, not a problem. But hold on a second here. F is not done yet, okay? This first invocation of sub1, which is called from F, is still in the middle of processing something. When subroutine G is preempting subroutine, thread B is preempting thread A, and subroutine G is also calling sub1. So without the proper understanding of local variables and parameters are on a per invocation basis, now we have a problem, because the second call of sub1 from G from thread B is going to overwrite stuff of the first invocation of sub1 called from F from thread A. But if they're on a per invocation basis, that the two invocations of someone, one from F in thread A and the other one from function G of thread B, they have absolutely nothing to do with each other. And that's why a proper understanding of local variables and parameters is actually very important when it comes to multi-threading type of programming. And this tells you that without you doing anything special, the way we declare local variables is already multi-threading friendly, which means that's not an issue. No issues whatsoever. Yep.
Is the amount of cores processor that are implemented the amount of threads that can be run this, say, if it's dual cores only, threads can be run?
That's a kind of tricky question because it depends on whether you look at it from the pretended perspective or whether you look at the actual perspective. When you look at the pretense, like how many threads can be running, quote unquote, running at the same time, it has nothing to do with the number of cores or processors. So you can have the simplest processor, single core, no hyper-threading and whatnot, and the operating system can create the illusion that you can have as many threads as you want. Only one thread can be quote-unquote active at any particular time. So when you run thread B, thread A has to be stopped. When you run thread C, thread B has to be stopped. Only one thread can be active at any particular time. Now when you run that particular scenario in a multi-core type of scenario, then thread A, B, and C can all be happening at exactly the same time. Because core 1 or core 0 can run thread A, core 1 can run thread B, and then core 2 can run thread C, and they can all be happening at the same time. So is that kind of answering your question? And hyper-threading also adds something to it too, because hyper-threading makes it more efficient to switch between threads, to basically utilize resources a little bit better. So that's why when you have hyper-threading on an Intel processor, the amount of the number of cores that shows up on certain operating systems basically doubles. So if you have a dual-core processor but with hyper-threading, Linux will report that you have 4 cores. But the actual efficiency is not quite the same as 4 cores, but it's better than actually 2 cores. Yep. I'm not taking roll anymore. It's too late in the semester to take roll. Yep. Well, we have got past that time already. All right. So that's basically what subroutines are all about. Okay. So the mechanism and the syntax of defining a subroutine is not really all that much. The biggest issue with subroutines is how do you structure the subroutines. So after this, we already talked about modular design. This is one thing that we have already talked about. I will briefly talk about this because this is mostly stuff that we have talked about. There are one topic that we haven't really talked about, but the other ones we kind of have talked about already. Top-down development in the implementation of functions. Now this is actually copied from the curriculum of this class. The curriculum of a class basically kind of dictates what topic has to be included in a class. So I'm going to have to include it. And the way I'm going to talk about this is, I do not agree.
Me too.
And that happens, okay? Because the way this is saying is, using top-down development in the implementation of functions seems to suggest this is the only right way to structure a program. And that is not the case. There's no single right way of writing a program. Okay, so before we talk about why that is not the only right way to do something, let's talk about what is top-down. Top-down is easy to understand. I'm going to do the same thing as I do in cisp360, so some of you have seen this already. So when you go to maps.google.com, okay, and let's zoom all the way out. Okay, it's remembering this because I signed it already and it kind of knows my location. So, there we go. That's pretty good. I mean, Google Maps cannot, get out of Earth. It's not Google Earth. So this is pretty much as far out as I can zoom out. This is the top view. Okay, it's a top view of the entire, Earth. Okay, so if I am to locate, okay, I have to pick something that you guys are not familiar with, just so that you can understand the concept. So let's say I want to go to the Cosmopolitan Hotel in Hong Kong. Okay, so I think it will be pretty hard pressed to find someone in this class that can pinpoint exactly that location without looking in the map. Well, I can, but that's the whole point. Okay, I'm the only person who can in this class. All right, so what do you do with this map here? I want to locate the Cosmopolitan Hotel in Hong Kong. What are you gonna do? Look up countries. Okay, so let's say if I I cannot. Googling it is not an option. Okay, because I know most of you are gonna go like, oh, I just select Cosmopolitan Hotel, right click, and Google search it. Okay, that's not gonna work. Okay. Okay, so the first question is, which countries do they belong to? Okay, that would be a valid question. Okay, for those of you who don't know that Hong Kong is a region in China, that's a legitimate question. But with all the protesting, the recent thing that has been developing, I think most people are now understanding, oh, that's a part of China, right? Okay, so it is China here. So that means I don't have to look anywhere else, okay? I'm not going to go to Alaska and look for Hong Kong. I'm not going to South America to look for Hong Kong, or Africa, or Asia, or Europe, or Russia, right? That's top-down design right there. Okay, it's top-down because I can ignore majority of the top-level map in order to locate one thing. Okay, and I don't have to know a lot of things about the other regions of the world. Okay, I have no need to know what is the capital of India, for instance, if I'm just looking for Hong Kong. Is that making any sense? Okay. All right, great. So now we know it is in Hong Kong. Hong Kong is in China. So what do? We zoom in. Okay, so we zoom in, and and I can tell you that Hong Kong. Well, you can see it right here. But that's also top-down design. Is at each level of a top-down design hierarchy, you only have a certain number of names or concepts or constructs that you can see at that point. It usually is a number that you can mentally, track. It won't be like 20 gazillion things. Okay, it won't be 500 things. So can you give me a rough number of things that we can see on the screen right now, like names?
China.
25. I would say between 20 and 40. Okay, would that be a right order of magnitude? Okay, and most of us can scan through like 40 items fairly quickly and locate one thing. Does that make any sense? Okay. And that's top-down design too, because at each level of a top-down design hierarchy, you want to limit the number of things that you need to track. Okay. So if there are only about 40 things on screen right now, does that mean that China only has about 40 cities? Well, if you can pack 1.7 billion people into 40 cities, then those must be really, really, really big cities, right? Okay, so that's the other aspect of top-down design, okay? It's just that, we are hiding information at each level and say that, okay, you probably don't need to know all the details. I'm going to only show you the important parts. Okay, that's also a part of top-down design. But since we can locate Hong Kong, let's go there, right? Okay, so I'm zooming in some more. And remember, each time I zoom in, it is going down one level in the top-down design hierarchy. And you can also see that right now, the number of names on the screen, it's still remaining to be about 20 to 40. Okay, it's never going to be something that is manageable. Now, this is only doable because of Google Maps. If I don't use Google Maps and I actually go to AAA to check out a real physical map, that's going to have a lot of names on it and make finding something really, really difficult. That is the equivalent of not having top-down design hierarchy, because now you have like hundreds of names on one single map and you have to locate one thing out of the hundreds of names. That's going to take a lot longer. Okay? All right, so now that we see that Hong Kong is here, the shape of Hong Kong is now starting to, to form. Okay, so what if I tell you that the hotel is on Hong Kong Island? Okay, so where are you gonna look next? The island, right? There are several islands, but each one is already labeled. So you know that you're not going to go to the Lantau Island, which is here, to locate the hotel. You're not going to go to here to locate a hotel because it's not even an island, right? So we know it's on this island here, so we can now zoom into the island. And that's the Hong Kong Island. And you can see with the Hong Kong Island, the number of names is once again, in the order of teens, okay? Maybe 20 names or so, okay? So what if I tell you the hotel is close to Happy Valley? Hey, that's one of the names here. I can locate it, okay? Sorry? Google Translate. Well, Happy Valley is called Happy Valley because they have the, what do you call that? Horse racing, okay? The horse racing track is in Happy Valley. And it's called Happy Valley because most people who go gambling, kind of like that name, of Happy Valley. The Chinese translation is literally horse racing land. I mean, that really is the translation. All right, so we are getting closer, okay? And once again, we are not looking at a very small, tiny spot on Earth, okay? And it is still showing about 20 to 40 names on the screen, right? And if I tell you it's right next to Queen Elizabeth Stadium, how long would it take you to find that? Not long, maybe about 10 seconds. If you are not familiar with the map at all, maybe 20, 30 seconds or so. Yeah, there are 7-Elevens, yes. So now we zoom in, and guess what? So now we can see Cosmopolitan Hotel. That's where it is. Okay, so question is, what kind of detail are we looking at this point using the entire Earth as the context? Extremely fine detail, like one line or several lines of code in a program that has 15 million lines of source code. Okay, this is how complex programs are organized. Okay, you can locate a few lines of code because of the hierarchy of top-down design. Okay. Are there any questions about this little analogy? Questions? Okay. Can someone tell me again what is the whole idea? Why do we like top-down design instead of not having top-down design? Just bombarding you with hundreds and hundreds and hundreds of names on each level of the map. Easy to locate. Go ahead. Readability, exactly. Okay, it's readability. Okay, but I have a problem here. Okay, because we can only display 20 to 40 things on the screen at any particular time. And China has thousands, probably at least thousands of cities. How do I find one? I mean, how do I locate the city in a particular place? Go by regions, provinces, regions, and then down to the cities, right? So we know the hierarchy, okay? We go by the bigger identifier first and say, okay, you're telling me to locate something. Which city does it belong to? Okay, I can, okay, but that city is not showing up on the map, okay? So can you tell me which province that belongs to? Well, that province is not showing up on the map either. Can you tell me which part of the country it is belonging to? Okay, now I can see, okay, that's the south side, north side of the country. We can now zoom into that particular region of a country. So that's how we can locate things using the top-down design. To compare top-down design versus not top-down design or no top-down design, think about all the thousands, if not tens or hundreds of thousands of digital pictures that you have taken in the past, say, 5 or 6 years. How do you organize those pictures? Okay. Well, I mean, but the point is, you guys all said buy something. Okay, nobody is going to upload all the pictures, stash it into one single folder, and say I'm done. Because if you do it that way, let's say you have 20,000 pictures, taken in the past 5 years. Okay, how are you going to locate a particular picture? That will be pretty hard, right? And I can tell you one way to do it, and most people probably won't like it. You crowdsource it. You open up your thousands of pictures on the internet, and you tell people, I would like to find blah, and then have people to go about doing it. And there will be tons of people who are more than willing to help you going through your pictures to look for a particular item. And all you have to do is to say, a few of those pictures are selfies, right? Then there will be like millions upon millions of people going through every single file, even though you're just I'm looking for that picture with a red rose in a blue vase, and that's what I'm looking for. And you can crowdsource it, and then you have millions of people looking through the pictures for you, and you have the answer in no time. That's how, what is that name? Capture? Okay, when you sign up for an account on the many places, they will give you like a piece of text that is really hard to read. What is that? Capture, right? So that is interesting because that's actually crowdsourcing. Yeah, it's really interesting. It's called capture. How do you spell it?
Capture?
Capture. Yeah, there we go.
It's got a T.
There we go. Okay, so capture is actually very interesting because what they do is they give you usually two pieces of text. One is coming from a digital picture of a digitization of a book or some kind of publication that Google is having problem translating automatically into the text. It's saying, oh, this is confusing. My OCR, optical character recognition engine, is having problem understanding what it is. The other one, on the other hand, is something that is generated. It's kind of obscured a little bit, but it's generated to let you, to make sure that you are actually a person on the other side. So what Google does is they look at the answer of both. If you are answering the generated part correctly, then Google has a fairly high confidence level that is the both images are processed by an actual person instead of randomly guessing, right? So what it would do then, it will capture your answer to the fuzzy picture also, and it would do this to many people, okay, million times a day and so on and so forth. So basically, Google is using the generated image as a filter to filter out robots, engines that are doing this automatically, down to actual things that the people are actually interpreting. Then they can look at the accuracy of the humans, interpreted images, and pick, let's say, the top 20%, okay? And they say, okay, these 20% of answers are completely spot on for the generated part. Let me see what they have to say about the fuzzy picture part. And they voted using that. So now, Google say, okay, great. Now we have, let's say 50,000 people looking at the same fuzzy image, and they all agree this is saying, GBT or whatever, okay, license plate or whatever, okay, and it would just say, okay, now I have a pretty high confidence level that is what the picture is about. That is actually the nature of capture. It's not just for making sure that you're not a robot signing up for accounts for spamming purposes. It's also a way for Google to read text that cannot be processed by a computer. And you're not getting paid for it. But it's ingenious. If you think about it, it's actually a very ingenious way of getting something done because you're now utilizing millions and millions of people to do a particular job. All right, so go ahead.
Another way I wanted to mention, like for finding the cities, it's kind of old-fashioned by grids,
Right.
There's A1, B1, and every map built with a grid on it. There's
Yep.
another grid.
And that is still top down because at the top level grid, you probably have a choice of, let's say, 100 grids, right? But that grid, when you look at it, it explodes into 100 grid all by itself, and you take one of those grids, it explodes to 100 grids too. So that's also a very good example of top-down design. Okay, so if top-down design is so great, why do I have a problem with this statement here? Let's take a look at this statement again. Using top-down development in the implementation of functions. Top-down is a terrific way of organizing something. Now, when I say organizing something, it means breaking a program that you're going to write into parts. It's just like structuring your English writing paper. Okay, you break it down into big sections first, and then within each big section, you break it down into smaller sections, and that's a great way of thinking and organizing things so that when you have a thought, when you talk to someone about the topic that you're supposed to write on, and somebody gave you an idea like, oh, I think blah 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 blah, or oh, you know what, I know as a fact that this is the truth. Okay, a little bit of fact that you think, hey, you know what, I can use that in my paper. So what do? You don't write off. You don't just write the sentence right away and put it into your article, right? You just throw that idea into the right bin into your article, and you just say, okay, I'll organize everything later on. That is top-down organization. So if it is such a great tool for organization, what about implementation? What is implementation? When in the context of software writing programs, what is implementation? No. It's not reusing it. Implementation is the actual development of code. So you're actually writing implementation. The term implementation is basically writing code. Not organization so much, but actually writing code. Now when you write code top-down, it's suddenly not such a great idea anymore. How do you test a program written in a top-down fashion? But how do you test it? Okay, so let me give you an idea. Okay, so based on top-down organization, I know that function f is supposed to call function A, function B, and function C, and I know exactly how to organize function A, B, and C. It has to call A first, and depending on the return value of B, sometimes it calls C. I know that part already. How do I test it? No C out for programming. No. Seriously, how do we debug a program like that? You cannot. Because what about A? Well, A is not written yet. Remember, we are talking about top-down design. So we are looking at things from the top view. A is not implemented yet. B is not implemented yet. C is not implemented yet. So at this point, I have no way to test the actual program from the top level. Okay, fine. Let's not test it, right? Now we focus on subroutine A. So by analyzing what subroutine A is supposed to do, I can now break it down and say, oh, you know what? Subroutine A is supposed to call F, G, and H in this particular order with this logic here. How do I debug subroutine A? Can't do it because subroutine F, G, and H are not implemented yet. Are you seeing my point? I look at subroutine F, same thing. So I will have to keep doing this, drill all the way down to one subroutine where I can actually write C++ code. And then what can I do? Nothing. Because none of the other subroutines is done. Okay? So by the time I have enough code to do debugging at the top level, I will probably have thousands, if not tens or hundreds of thousands of lines that are not previously tested yet. And that's not the best way of doing things. It's a great way of organizing something. It's not such a good idea to test something. Now let me give you another idea of why what is top-down design. Let's say we are designing an engine, new type of car engine. Okay, so I have this great idea of how to design a new car engine. It's super efficient and so on and so forth. Okay. At the top level, I can now break down the components into, okay, this is the mechanical part that will do A, this is the mechanical part that will do B, and this is the electronic control system that will do C. Great, okay, I have a modular design, each one is kind of individual, they have well-defined interfaces. Can I debug it? Can I test the engine? No, because they don't work, right? Each one is just is an abstract concept. So I work on one particular part, let's say the electronic part, okay? I break it down into subcomponents. Can I test those subcomponents? No, because each one is an abstract concept. So I actually have to design something down to the transistor level or circuit board level. Then I have something. But then I cannot test it either because I don't have the other components to test it with. So by the time I have all the components back, I have a finished, quote-unquote, finished engine, right? But how many components of that finished engine have not been previously tested? All of it. I'm not gonna, I will not stand in that room when someone starts their engine. Because nothing is tested yet. Go ahead.
With that analogy though, aren't the electronics tested before they are implemented with the mechanical A and mechanical B?
But then you're not using top-down anymore.
No, but I understand, but you write
That is the whole point. You're right. You're absolutely right. Okay, the electronic component needs to be tested by itself, but you're now at the bottom level of the top-down hierarchy. You're at a very low level here. So you're really not using top-down anymore. You're using top-down to guide you to the component. But when you're actually implementing, when you're making something to make the engine, you're actually doing it in a bottom-up fashion. Am I making any sense here? So that means top-down is a terrific way of looking at things, organizing things, but it's not such a great idea when it's actually time to implement something. In terms of implementation, it's a combination of top-down and bottom-up. Okay? Bottom-up simply means that you're implementing the lowest possible level thing and test it. Now, it's easy to test, right? If I have a sub-circuit board and its only function is to test whether a probe is hot enough at a certain temperature and trip the output to, say, okay, on, okay? That's pretty easy to test. I mean, I can stick that, probe, into a flame or, heat it, whatever thing that is controlled and heated and say, okay, the input temperature is now at, 600, Kelvin. Is the output, actuated? I can see it's actuated. And if I drop the temperature back to a certain threshold, is it turning off the output? Yes. I can test it. So I can make the circuit, I can test it, and then I can say, this component is now done. But that component is a very small, tiny little part of the entire engine. So what do I do next? Use this component for the next level up design. Then I can test it again. So when you're testing and implementing program, bottom up is a great way of doing it because once you debug and verify the lowest possible level of functions are working, then you have a solid foundation to build up the next level of functions without having to worry about, oh, if it's not working, can it be the subroutine that I'm calling? No, because you have already tested those subroutines on their own. So that's why I have a little bit of a problem with this particular statement because it seems to imply that in the implementation, top-down is the only way or the only right way of doing it. But in reality, it is not always the case. Okay, so we are running out of time today. We'll continue this on Wednesday and we'll kind of talk about the key to the exam too.